Go ahead, Deepak.
Thanks. Thanks everyone for joining. I'll start with a quick introduction. My name is Deepak Kodihali. I work with IBM and I've been contributing to the OpenBMC project since 2017. I'm based out of Bangalore in India, and I have my mailing list, email ID, and IRC nick here in case anyone wants to reach out for questions related to OpenBMC or PLDM. I maintain the OpenBMC PLDM repository, and today's talk is going to be about PLDM, which stands for Platform Level Data Model. We'll look at what that is. So the agenda for today, a little bit of introduction on PLDM and kind of the motivation to use PLDM. Then we'll look at some of the key features of the PLDM specifications. Then a look at what's present in the OpenBMC PLDM stack currently. Okay, so first of all, DMTF has a white paper which talks about guidelines for interoperable management of systems such as servers. Some of the goals here are basically to move away from legacy and proprietary management solutions, which were mostly OEM extensions or tools built over the least common denominator then, which was the IPMI spec. So this kind of migration towards modern protocols is happening not only for out-of-band management, where we tend to see migration from IPMI to Redfish, but also for inside the box or in-band management, which is where some of the PMCI protocols come into picture and can act as a replacement for in-band IPMI. And this kind of change is what motivates that is the use of industry standard hardware and interoperability between the hardware, and this is well suited for hyperconverged data centers, etc. I have a link here to the DMTF guidelines. The specs that are called out by these guidelines are Redfish, SMBIOS, and the host of PMCI specs or protocols, PLDM being one of them. By the way, feel free to stop me at any point of time if you have questions. So let's look at the PMCI stack, or rather the PMCI protocols for inside the box communication. As you can see here, the BMC is kind of the center of the world, and there are a set of protocols defined that are meant to work over standard host or physical interfaces. For example, there's the management controller talking to the platform software, which could be BIOS or OS or hypervisors, for example. The typical interfaces defined there are, let's say, serial and KCS. Although there is talk of kind of deprecating those in favor of more modern interfaces such as PCIe or Redfish host interface. That's also mentioned here. But the BMC and the host firmware can talk PLDM over another transport layer protocol called MCTP, which we'll look at. And the MCTP protocol can bind to these host interfaces such as serial or KCS or even PCIe vendor-defined messages. Then there's PMCI also covers the management controller talking to other management controllers, and also the management controller talking to managed devices or smart devices. Examples of those are network controllers, where you have, for example, the NCSI spec, NCSI over RBT, and other kinds of managed devices, storage drives, sensor chips, etc. And commonly used physical interfaces there are PCIe and SMBus. MCTP, which is the transport layer protocol, can also run on top of these physical interfaces, and then the management controller can talk PLDM over MCTP to talk to these devices. The MC and the NC, the network controller, there's of course NCSI spec that's used there, but the management controller can also talk PLDM to the network controller for things like firmware update, for example. Also shown here is the out of band set of specifications, which is Redfish being the popular one there. This is basically a different view of the PMCI stack, and this also the intent is to also talk about what's currently implemented in OpenBMC. So PMCI, the stack is basically layered. As you can see here, there's a set of upper layer protocols, PLDM being one of them. But there are other protocols such as MCTP control and SPDM. I wouldn't be getting into details of protocols like MCTP and SPDM or NCSI today. I believe there are separate sessions for those. But these are a set of upper layer protocols which deal with typical use cases that exist in band or inside the box communication. These protocols run on top of transport layer protocols such as MCTP or RBT. And the MCTP protocol further has what's known as binding specifications that lets the MCTP protocol deal with the specifics of physical layers, physical layer interconnects such as SMBus or PCIe, etc. The idea with the layered architecture is for example, the upper layer protocols can be agnostic of the physical layer bindings, and it should also be possible to introduce newer generation physical interconnects, let's say such as I3C, into this model without impacting the upper layer protocols or even the MCTP, the core layer of MCTP. This was kind of difficult to do with IPMI because of IPMI's system or hardware interfaces. BT and KCS were kind of tightly coupled with the protocol. In terms of the PLDM itself, PLDM is actually a set of specifications that are mentioned that you can see here at the top left. Each of the specifications is actually a PLDM type that has a number assigned to it. And the purpose of having separate specifications is to is to have each spec tackle a certain set of use cases and functionality. For example, there is a PLDM for SM BIOS exchange specification. There is PLDM for monitoring and control, the type 2 spec, which deals with sensors and effectors for use cases such as power and thermal control, LED control, state control, and several other monitoring and control type of use cases. There is a spec dedicated for BIOS control and configuration between the BIOS and the management controller. This deals with things like exchange of BIOS tables, updating BIOS settings, and so on. There is a PLDM fru format and a specification which has a set of commands to enable fru exchange between two PLDM devices. There is PLDM for firmware update, PLDM for Redfish device enablement, which is a fairly new spec. The idea there is to have BMC relay Redfish requests to connected devices over PLDM, so that the connected devices really don't have to implement something like a TCP/IP stack or JSON. PLDM can be used as PLDM along with binary encoded JSON can be used as the transport to relay redfish requests. I've also highlighted here a PLDM for file IO specification. This is something that IBM and other companies are working with PMCI for to see if this can become a standard. At the moment in the OpenBMC stack, this exists as an OEM IBM extension. And this is to enable certain use cases such as exchanging error logs between the host firmware and the BMC, offloading diagnostic dumps, and so on.
Just a quick question, Deepak.
Yes.
So the MCTP over LPC and the PLDM file, they are blue color. Is there any significance for this color?
Yeah. Thanks for asking that. I should have pointed that out. Neither of these are standard PLDM specifications yet. These exist as OEM extensions, but it's something that we can talk to PMCI about to see if there's interest in standardizing them.
Oh, okay. And for the file IO, you mentioned loading host firmware images, right? So how does that is different compared to the firmware update? You have type 5, which is a firmware update.
It's slightly different. There isn't really an update here. It's the use case is typically for platforms where the host firmware doesn't have a dedicated storage of its own and kind of relies on the BMC to be able to read its own image. So there's typically some early stage bootloader that then can read the rest of the host firmware stack, which is stored as, let's say, a bunch of files on the BMC.
Okay, so it's not like a real update, but it's more like a storing the image on BMC.
Right.
Serving as a file.
Yep.
Got it. Thank you.
All right. So moving on, let's look at some of the PLDM specifications. So there are, I think, 10 of them. In the next couple of slides, we'll look at some of the key highlights of a few of the specs. So I wouldn't really go through each of the specifications. So the first three here, the PLDM base specification, the IDE and codes, and the state set specification, these are kind of foundational specs on top of which the other specs are built. The PLDM base specification has the PLDM message structure or the packet structure. The PLDM state set specification talks about defines standard state values for things like boot states, path thermal states, and so on. And as we saw in the previous slide, there is a spec for true data specification, SymBIOS, BIOS settings, monitoring and control for states and control, firmware updates specification, RDE, and PLDM or MCTP binding. As it is with most DMTF specifications, each of these specifications, there's a DSP number assigned to the specification. So this is from the PLDM base specification, the structure of a PLDM message. So there's 3 or 4 bytes of header based on whether the message is a request or a response. In case it's a response message, there's this byte 4, which is the completion code. But otherwise, there's information about the first byte describes whether it's a request or a response, and there is an instance ID for every PLDM request message that lets us map responses to requests. Then there is a PLDM type, which essentially points to a specific PLDM profile or specification, such as BIOS or FRU. Each of these specifications defines a set of commands, and the command code is defined in byte 3. a sort of a common observation in across PLDM specifications is the specifications comprise of a data model that is specific to the function. For example, a data model for fru or BIOS, firmware update, and so on. Along with the data model exists a set of commands that enable access and modification of the data model. So apart from the header information, there can be payload 0 or more bytes based on a specific command. This is also from the PLDM base specification. So in PLDM, there is a request response model, a PLDM entity, or let's say a device that's running the PLDM stack can be a requester or a responder. I think the names are self-explanatory. This diagram depicts typical PLDM-based discovery. So actually, prior to this, before the requester and responder talk to each other, there's definitely the underlying transport layer based discovery as well. Without getting into too much detail, if PLDM was running on top of MCTP, then there would be the responder in this case, for example, would have an MCTP EID or an endpoint ID, which can be either statically allocated or it can be allocated by the MCTP on the requester side. You can think of the MCTP EID as an IP address, for example. So the entity, which is the requester, knows how to route upper layer requests, which in this case is PLDM, to the MCTP EID, which belongs to the responder, and that routing responsibility lies with the MCTP layer. Given we have that, PLDM discovery typically comprises of getting something known as the TID or the terminus ID of the responder. The way this helps is there can also be asynchronous PLDM messages or alerts basically that can be emitted by a responder to a requester. The terminus ID is included as part of the event, and that lets requester determine from which terminus an event is emitted from. So that's why the getting the TID becomes important. But after that, there are a bunch of commands that are defined in the PLDM base spec that can be used here to essentially determine capabilities of the responder. So the get PLDM types indicates all the PLDM types or specifications that the stack on the responder side implements. The version for a particular type can also be determined via the get PLDM version request. And finally, for a given PLDM type and version, the set of commands that are implemented by the responder can be retrieved as well. So I think another key aspect of the PLDM spec is the PLDM entity. MNC stands for monitoring and control here. So PLDM entities are described in detail in the PLDM monitoring and control spec. So almost everything in the PLDM model across different specs is related to an entity. So what I mean by that is sensors or effectors. Effectors are a way to control things. For example, state of a boot or let's say fan speed and so on. So effectors and sensors are related to entities, entities like fans or a CPU. Similarly, fru information is also related to an entity, the entity being the fru itself. The fru information, for example, being present on an EEPROM card, and that EEPROM being associated with an entity which is the fru. That diagram on the left indicates various entities. And entities can be physical or logical. So what's shown here is a system which can be thought of as a logical entity which has a physical chassis. Also encoded in the entity information is the instance number of the entity. So there's one physical chassis here, which under which there is a logical, the concept of a logical power supply, which actually is comprised of a couple of power supplies with entity instances 1 and 2. There are temperature sensors on both of them. The number here, 14 and 18, for example, can be the sensor ID of these temperature sensors. There is also a redundancy status, which can be a sensor. There are a couple of physical fans. So each of these would be physical or logical entities. And there is an entity type for each entity, which is 6-byte information comprising of the entity ID. So earlier we saw I mentioned the PLDM state spec and the entity and ID code spec. So different entity IDs are defined in these specifications. There are a large number of entity IDs defined for common entities such as CPUs, DIMMs, motherboards, and so on. There's a PL physical logical bit that tells us whether the entity is physical or logical. There is an entity instance number, a couple of bytes for that, and there is the concept of a container ID, which helps us form relations between entities. We'll look at an example for that. So one thing that stands out here is PLDM does scale better than IPMI. Because the IPMI sensor is a byte wide. In PLDM, there's a 2-byte. The sensor IDs can span the 2-byte sensor ID, and same goes for the entity instance number as well.
Quick question here. So when you're saying that entities, and there is something called PLDM type, which is like you said, fru or a sensor. So this entity is under that. So can same fru type have multiple entities?
Sure. So I mean, in this case, if you look at this diagram here, the chassis, if you consider the chassis as a fru, then it is composed of multiple entities here. The power supply, the physical power supply 1 and physical power supply 2 are separate, distinct entities. They'll have the same entity ID because they're power supplies, but they'll have different entity instance numbers. So that kind of composition is possible.
But all of them will have same PLDM type.
So when I say PLDM type, it's this. It's this number, type 0, type 1, type 2. It's actually the number that's associated with a PLDM specification. So the PLDM type is different than the entity type that I've mentioned here. The entity type is a collection of these three or these the 6-byte entity, basically, that's composed of the entity ID, the entity instance number, and the container ID.
But each device can have multiple PLDM type. It can only have one PLDM type, right?
Right. There isn't a PLDM type association with the device. Okay. Because the PLDM type is the specification itself. So each device can implement multiple PLDM types or may not implement all the PLDM types.
Okay.
A quick question on the entity ID. So is this a predefined entity IDs? Like say like IPMI has this power supply, fan, temperature. There are like predefined, right? So
yeah, there are a set of defined IDs, and there are reservations for OEM as well. Yes.
Okay. Okay.
Right. Moving on to the next slide. So another important aspect of, again, the MNC spec, but which is kind of pervasive across specs is the concept of platform descriptor records, or PDRs. I think conceptually this is similar to an IPMI SDR in the sense that PDRs describe metadata, or PDRs are metadata that help you describe things like units in case of a sensor, in case of temperature sensor. And they also help denote relations between PLDM entities. We'll look at specific examples in the next slide. What's shown in this diagram here is the notion of a primary or a main PDR repository, which is typically on the MC. As part of initialization and discovery, the MC would retrieve PDRs, let's say, of connected devices. The diagram here shows a couple of connected devices. The MC would retrieve PDRs out of those devices and add them to its repository. This helps the MC later on for any kind of monitoring and control. Also, event messages coming in from these devices will contain a terminus ID, and there is a PDR that also called the terminus locator PDR that's shown here, which helps the MC map a TID to a specific PLDM terminus.
Question.
Sure.
So the sensors, let's say we have LM75 or TMP75 sensors. Would PLDM work on those or not?
It depends whether what's containing those sensors. I mean, when you say PLDM would work on or not, would you mean if you send a PLDM request to?
Yeah, so it probably wouldn't work because it's a passive device, right?
Right.
It doesn't respond to MCDP version or the basic command. If it only responds to the basic command, then only the sensors can be added to the PLDM PDRs, right? Or is there a way to kind of map those sensors to the PLDM PDR if they can't respond to MCDP, if they are not MCDP compatible?
Right. I mean, I would suspect there would have to be another intelligent entity which implements this spec and can provide information about the sensors on which the entity can access,
Okay.
and add it to its own PDR model.
Yeah, and the purpose of asking this question was we'll still need the IPMI until that option is kind of there, right? Otherwise, this PLDM can cater only to a limited number of smart sensors, not to the passive sensors like LM75 or TMP75, unless they are controlled by a microcontroller.
Unless they are controlled by a microcontroller. That's true when it comes to sensors. Yes.
Okay. Thanks.
So quick question on that is if they can, if they are supported by microcontroller also, but they still need to implement the PLDM model, right, in the firmware.
Yes.
And they don't need an MCTP. They can still work on SM bias on I2C.
Yeah, there is an MCTP over SM bus binding. So
okay.
The PMCI model requires you to PLDM typically runs on top of the intermediate MCTP protocol, which can run over SMS.
Okay.
Yeah, sorry, one more to add to Vijay's point. I guess MCTP or SM bus, even if that's implemented, the firmware on the other side should respond to MCTP version command, basically saying that I'm MCTP compatible, right?
Right.
Yeah. Okay.
So mainly PLDM is tied to the MCTP. So no matter what, if we have to have PLDM as well as MCTP capabilities in the firmware of the device.
I think that is typical. There is also PLDM over RBT. Although I'm not very sure on the class of devices that implement that model.
Yeah, the NIC supports it. The current Mellanox and Broadcom NICs, they support the PLDM over RBT.
Right. Okay. Thanks, Sai. All right, moving on to the next slide. So here there is just an example of PDRs. There are actually several PDR types defined in the MNC spec. There are few examples here related to the same diagram that we had in the previous slide. So there is a numeric sensor PDR, and here you can see the entity information tells us that the entity type is physical power supply entity instance number 2, and there's a container ID for the same. There's a sensor here with ID 14, and the unit here is degree centigrade. There is a fru record set PDR as well associated with the power supply. So basically there's an EEPROM somewhere that has information that would have a PLDM fru format stored on that EEPROM. The fru format will have one of the fields as the fru record set identifier, which shows up here. So that would let firmware map the fru format or the fru table to the PDR to help to determine what type of fru is the fru information related to. And similarly, the kind of relationship or hierarchy present here can be depicted using what's known as, the name's missing here, but it's called the entity association PDR. So that kind of helps us build a tree of all the fru and entity hierarchies in the system, as shown in this last diagram here, with the system being the root, and then there's the chassis, which contains a couple of power supplies and so on. So next, let's briefly look at what's currently present on the PLDM stack on OpenBMC, some of the components. So the stack which is on GitHub, with the URL is present here, has certain components. We'll look at these individually as well in subsequent slides, but there is something called libPLDM, which is the main protocol library. There's a PLDM or MCTP daemon. There's an optional libPLDM responder, which is specifically for the case where the BMC is acting as a PLDM responder. This might not be very typical, but on IBM platforms, we have this use case where the host can act as a PLDM requester, and likely this is also a case where BMCs are talking to each other. There is PLDM tool, which is basically a PLDM requester tool, and we use that to test PLDM responder implementations. Then there is a way to conditionally compile OEM extensions. Let's look at the components a little bit in detail. So libPLDM, this is basically the protocol library that's written in C. It's platform agnostic, meaning the goal is to be able to reuse this outside OpenBMC and likely on non-BMC based platforms as well. For example, on IBM platforms, the host firmware stacks make use of libPLDM. libPLDM mainly has encoder and decoder APIs. Basically, given a set of input, libPLDM can encode a certain PLDM command message. Basically, it serializes the input and outputs a well-formed PLDM request message. Similarly, or response message, and similarly, it can decode a PLDM message into individual pieces that form the message itself. That's at a very high level, but it also has other APIs specific to certain key areas. For example, there are APIs that help you construct and iterate a PDR repository. There are APIs for encoding and decoding fru table information and BIOS table information. The library handles NDNS. The PLDM specs are little endian. And finally, the goal of the kind of goal is to have the API separate from implementation. For example, today the PDRs are implemented as simple left child, right child kind of tree structure, but that could be changed to something more optimal, let's say like a red-black tree or something, without really changing the API. Next, the libPLDM responder. So this is, like I said, for the case where the BMC acts as a PLDM responder. libPLDM responder is a collection of handlers for incoming PLDM request messages coming into the BMC. Handlers based on commands and based on PLDM types. This is implemented in modern C++, and most of the command handlers talk dbus to other OpenBMC applications based on the specific function. There's also a set of in-repo JSON config files that help the responder, let's say, create PDRs or create fru records for the frus that the BMC has access to. And the config files help modify this as need be for different platforms. Moving on to the next slide. The PLDM daemon itself, it's basically a PLDM or MCTP daemon. There is an MCTP daemon also implemented on OpenBMC, which provides a Unix socket-based API that PLDM daemon uses to send out PLDM messages and to also listen into incoming PLDM messages. This daemon links with libPLDM and can optionally link with libPLDM responder as well. When the BMC can act as the PLDM responder, this daemon routes incoming PLDM request messages to the right handler.
Question. I believe there was an initiative to kind of use the MCTP driver in the kernel space. Is that what's the status on that?
I think that is still work in progress. Andrew Jeffrey would have the latest on that, but I still think that's on his list and it's work in progress.
So currently this PLDM daemon is kind of communicating with the MCTP daemon in the user space.
In the user space, yes. Yeah. Yes, that's right. And yes, there's then PLDM tool, which, like I said earlier, is basically a requester tool. When run on the BMC, it can target the BMC, the implementation of the responder stack on the BMC itself, or given an MCTP EID, it can send out messages to connected PLDM entities. And this kind of helps us because it lets us test stuff, let's say on a connected device, even before we've written some of the PLDM requester code on our side. So I just have some snapshots here of the tool running on the Tacoma platform. So there's here you can see the PLDM tool basically trying to get the PLDM types that are implemented on the BMC itself, and this is the same thing in raw format. And on the right here, there is an invitation on the BMC to read the first PDR, and the same here, although with an MCTP EID provided. So in this case, the request message is actually going out to the MCTP entity that has EID 9, and then the response back received back is parsed and shown in this format. There's the first PDR happens to be a state effective PDR.
So in case this PLDM tool talks to BMC only, so does this needs to go to the MCTP daemon, or just like simply PLDM daemon should be able to respond?
So in this case, so to keep the code consistent, it still uses the same interfaces. So it does actually talk to the MCTP demux daemon, but there isn't really a physical binding that comes into play here. So the MCTP demux daemon has this concept of a null binding, which is, you can think of it as loopback. So that's how it works.
So it's a separate daemon than the normal MCTP daemon?
It's the same. It's the regular MCTP daemon.
Okay.
So even in this case, the tool doesn't have to do anything different than the case here, meaning it does write the PLDM request message to the same MCTP daemon provided socket, although it makes use of a reserved EID that lets the MCTP demux daemon determine that this is like a loopback kind of thing. So the MCTP daemon then just relays that to a connected client, which happens to be the PLDM daemon.
Okay.
So to the PLDM daemon, it looks like, doesn't look any different than a request message coming in from some other MCTP entity.
So this PLDM daemon of the BMC will become a responder in this case, right?
Exactly. Yeah. Okay. Some of the future work in terms of things that we believe adds value to the PLDM stack is having the BMC act as a PLDM requester. There's some code for this today, but there's still a lot to be written, and this will be useful for the case where there are actually cards with firmware on them that implements PLDM and MCTP. PLDM based firmware update for that's not implemented today, but that's going to be useful for things like NICs. In fact, I recently saw an update in the 5.9 Linux kernel. There's actually the PLDM firmware update. There's a small library now that's in the kernel itself. So maybe we can leverage that. Redfish device enablement, which is actually a PLDM spec, can also be useful for devices that intend to participate in Redfish-based management without really having to, like I said earlier, implement JSON support or a network stack.
So the currently uses of PLDM in OpenBMC is via PLDM tool only, right?
No. So on IBM platforms, so I can talk from that perspective, the host and the BMC have moved away from in-band IPMI to PLDM.
So in that case, BMC has become a responder.
And requester as well. So we have use cases where things need to be initiated by the BMC. So there's some code for that as well, where the BMC acts as the requester.
Okay, but you mark as here future work. That's why I thought that's not available.
It's quite minimal today. When if there's actually interest in using PLDM to talk to connected devices or NICs or other BMCs, that needs a lot more work, because I think that kind of has to fit into the existing architecture in terms of using things like entity manager, because you'd have, let's say, entity manager detecting a platform which has these kind of devices which support PLDM, and then we would have to assign MCTP EIDs to those devices if they respond to MCTP, and then PLDM communication can happen with those devices. So that's what I mean in terms of future work. There's actually a session on this as well, I believe. Add-on got support using PLDM, so I think
yeah, Richard is going to go deep into that.
Right. So I believe some of this will be covered as part of that presentation as future work as well.
So as of now, where is the PLDM being used, or what are the available devices which supports PLDM stack, like a stack?
So I don't have with me like a comprehensive list, but some of like one of the things that I am aware of is what I pointed out already. Some of the NICs from Mellanox and NIC cards from Mellanox and Broadcom, they are PLDM enabled primarily for PLDM firmware update.
Yeah, those are the things that I know actually, but other devices we are not sure.
Yeah, but
yeah.
My question on that is, as I told that those devices supports the PLDM stacks, but do we have any client or who is really using that, or like because as you said in OpenBMC we are not even supporting those NIC getting the data over the PLDM. So if those devices are existing, then there has to be some client side request to also support it, which does get the data. So do we have end-to-end solution, any single piece where it is working?
So I believe there's code in Sai, you might know this better, but probably in the Facebook OpenBMC stack. Or,
Yeah. That's why I think this is in the future work, Vijay. So I think this item. So
Okay.
it has to be, somebody has to do it actually. So today there is some code in the Facebook, but it's very ad hoc. So
okay.
That's why I think it's in the future work section.
Okay.
So one more question. So Deepak, you mentioned on IBM platforms. So at least BMC is a PLDM terminus, as well as the host is a PLDM terminus right now, right?
Right.
Okay. So there aren't any other PLDM terminus that is kind of working, like maybe NIC?
No, not yet.
Okay. I guess you mentioned you're not using the standard host interface like MCTP or KCS or MCTP or serial, but you're using MCTP or LPC, is that right?
Yeah, that's right.
Okay. So with eSPI coming in, any plans to implement MCTP or eSPI as well?
Yeah, I mean, no plans as such, but so that's again, that's not an existing binding, right? That would be a new one as well.
Yeah, yeah. I guess with eSPI, yeah, there are some licensing issues as well. So
okay.
Great. Thanks a lot, Deepak. If
Thanks.
no other questions, I think I will stop recording. Thank you all.
Thanks.
thank you.